In this video, we are going to talk about functions of complex variables. This is our overview slide, which we'll spend about 5 minutes on before we go through each topic in more detail and more examples. First, we'll talk about functions of complex variables. Just as with real variables, complex variables can be related to one another using functions. So we have this function here, a complex variable w is a function of a complex variable z. And it's common to separate the real and imaginary parts of a function so that z is equal to a function, or if z is a complex number, then w of z is equal to u plus iv. That is a function u of xy that produces the real part of w of x plus iy, plus I and v, which produces the imaginary part of w x plus iy. And so we have this example here. So if w takes a complex number and produces its square, which is equal to, if we do this out, do the math out mathematically, we get x squared minus y squared plus 2ixy, then our real part of our function is this x squared minus y squared, and the imaginary part, the v that gets multiplied by I, will be 2xy. Next, we'll look at visualizing or graphing complex functions. Because it takes the entire plane to represent a single complex number, we can't just graph it where our domain is one axis and then our range, or our answer, f of x, is plotted on the y-axis, because we need both the x and y now to express our domain. So what we often do is use a z-plane, which is a complex plane that is our domain, and then we think of our function w as a mapping to go to a different complex plane, the w plane, which is our range. And so for our example, we'll look at z, which is a complex number, x plus iy, and our function w, which is equal to z squared. So when z is equal to -1, our w is equal to 1. So it'll take this -1 point, and it'll map it to the point 1. Similarly, z will take I, so I squared is -1, so it'll take this point here, I, and it'll map it to this point here. So it's a mapping. So it's not something we can directly graph on a two-dimensional space with two axes. There is a second, more abstract visualization, which is to plot the functions u of xy and v of xy as the real and imaginary components of w, but we won't spend much time on this. At this point, I'll also give you a few more examples of different types of graphing or functions of complex variables before we go into our last topic, which is extending the domain of elementary functions. So functions of real variables can be extended to deal with complex numbers. So for sine of z, we can extend the domain to not just be real numbers, but take complex numbers. And we do this using the Taylor series, which we had looked at in our previous video. We can do this for cosine as well, and e to the z, which we also did in our previous video. So we can extend e to the z, or e to the x, to complex numbers e to the z. From there, we get the Euler identity we looked at our last video, and also here, from there, we also have the exponent representation of a complex number. From sine and cosine, and then exponents, we get these formulas for sine, cosine, tangent, sinh, and cosh. And then finally, an important one we're going to look at is natural log. So that's our overview. So now we're ready to start back up and take a closer look at functions of complex variables. So as we had said, as with real variables, complex variables can be related to one another using a function. So if we have a complex variable w and a complex variable z, it may be that w and z may be related. In other words, w can be written as a function of our complex number z. The example we are going to use is w of z is equal to z squared. So w is related to z by being the square of z. So z squared, and I'm going to write this out, is equal to x plus iy times x plus iy. So I multiply these two x's, I get x squared. When I multiply this times this, I get x times iy. And then here, times this, I also get another x times iy, so I have I times 2xy, and then finally I have y squared, my y times y, but I also have I times I, which gives me this negative here. And next I'm going to add this comment. It's common to separate out the real and imaginary parts of the function. So I want to write z now, or w, of x of iy equals a real function, u of xy, plus I times another real function, v of xy. Looking at our example over here, so I'm going to group the things that are not multiplied by I, that's my x squared minus y squared, and then over here I'm going to group I times 2xy. So I can say that u now is equal to x squared minus y squared, and v is equal to 2xy. So I put it into this form over here, u of xy plus I of v of xy. And the significance of this is this u of xy and v of xy, they're real functions. These numbers x and y, these are real numbers. And then what they produce are real numbers. There's no complex numbers in here. So now we can analyze u of xy and v of xy as we did for our regular real numbers. Our next topic is going to be visualizing or graphing complex numbers. And I'm going to use my w of z equals z squared as my example. So here I chose some input for z, which is equal to x plus iy. So I chose negative 1i, negative I, 1 plus I, and 2 plus I. And then I calculated w of z, which is z squared, which I just took this formula here, my x squared minus y squared plus I times 2xy. So over here, when z is equal to negative 1, my x value is equal to 1, my y value is equal to 0. So x squared is minus 1 squared minus 0 squared plus 2, and I just wrote 0 because y is equal to 0. When you multiply it out, you're going to get 0, and you get 1. When I calculate for z equals I, in this case, x is equal to 0, y is equal to 1. So I have 0 squared minus 1 squared plus, and here I have my I, 2, and then since x is 0, I just put a 0 here, and I get negative 1. So be careful here. When you plug in y, sometimes I'm tempted to plug in an I, but really you want the coefficient in front of the y, which is 1. So it's the 1 you are squaring, not the I. Okay, so next we have, right, because the I here, it's x plus iy. Y is a real number. It's the coefficient in front of the I. Okay, so next I have negative I. So x is equal to 0 and y is negative 1. So I get 0 squared plus negative 1 squared plus I. Again, because x is 0, I just set this equal to 0. So my final answer is negative 1. 1 plus I, in this case x is 1 and y is equal to 1. So I have 1 squared minus 1 squared plus I times, now we have 2, x is equal to 1 and y is equal to 1. So my final answer here is just 2i. And finally I have 2 plus I. So x is equal to 2, y is equal to 1. So I have my 2 squared minus 1 squared plus I, 2 times, oh, this should be a 2 times 1. So this should be a 4i over here. And again, I'm going to give you my warning. When you put in y squared, for some reason it's so tempting just for me to put in I because it's the second term, but really it's the coefficient. Y is the coefficient in front of the I. The next thing I want to say, now if we want to plot this, we can't just plot this on the x-axis and these numbers on the y-axis, because to get these numbers, right, to get 1 plus I and 2i, this here needs an entire plane and this here needs an entire plane. So what we need to view this as being a mapping from this set to this set over here. So in other words, we think of this set then gets mapped, our domain, which is over here, the z values, gets mapped to another, a range, or the w plane over here. So we have negative 1 is mapped to 1. So I can also do my little arrows. Negative 1, ooh, maybe this is going to be messy. Negative 1 is going to be mapped to 1. And then my I over here is mapped to negative 1. So let me get I is here, gets mapped to -1. The next one is -I is also mapped to -1. Remember, that's okay for functions. You don't want one thing in the domain mapped to two things in the range, but multiple things from the domain can be mapped to a single value in the range. Now I have 1 plus I gets mapped to 2I. So 1 plus I is over here, and I want to map it to 2I. Oh, this is why I said it's going to get messy. And then I have my 2 plus I is going to be mapped 1 plus 4I. Maybe I'll do this in green. My 2 plus I is 1 plus 4I, which I have it graphed here incorrectly. So I'm going to try my 2 plus I gets mapped to 1 plus 4I. Sort of messy, but that's how you map. And you can imagine there are going to be other times where you'll map a curve in the z-plane, the complex plane over here, and maybe it'll map to a different curve, maybe even a circle. So it might be that this curve gets mapped to a circle or something, but you can, instead of going points, maybe you have an entire curve and you plug it in your function, and maybe you'll get a different curve over here in the W plane in the range. And because we've gone over this, and also because so much complex analysis involves writing, or is easier if you write your complex number in exponential form. Remember, exponential form means if you have this point here, which I'll just make it kind of blue, like this blue dot here, right over here in the graph, then what do we have? Then r is our distance from the origin, or our radius, and then this e to the I, the theta, is the angle in the counterclockwise direction, so in terms of increasing radians from the x-axis. Right, so here's our theta. So if we want to look at this same function where w of z is equal to z squared, so now w here is z, z squared is going to be r e to the I theta times r e to the I theta, which is just r squared e to the I 2 theta. Now using Euler's theorem, which I've written here, I had to move this graph down a little bit, but Euler's theorem, e to the I theta equals cosine theta plus I sine theta. So the r squared just multiplies through, so r squared, you get an r squared cosine theta, r squared I sine theta. And then the theta now is not theta, but 2 theta. So we have r squared cosine 2 theta plus I r squared sine 2 theta here. Now also I've written it this way because remember when we talked about often we like to write our function so that we have a u of xy plus I v of xy. That way u and v can be real valued functions. Here I've done exactly that. So now this is written as u of r theta is r squared cosine 2 theta. This is the real portion of our function. And the imaginary portion of our function, v of r theta, is equal to r squared sine 2 theta. And why I say imaginary part of our function, this is actually a real valued function. R and theta are real, and r squared sine 2 theta is real, but it's the portion that gets multiplied by I. That's why I say the imaginary portion. I want to continue with this example here to show you what this mapping looks like. So let's just take this one point here as our example. The point I have here, which is 1, 1. So for 1, 1, or 1 plus I, our r is the square root of x squared plus y squared, which is square root of 1 plus 1, which is square root of 2. And now our theta, I can use the tangent formula, but I also know that theta, right, the whole entire circle is 2 pi, so half a circle is pi, which means a quarter of a circle is pi over 2, which means this, because it's 1, 1, is half of pi over 2. So theta is going to be equal to pi over 4. So some of these, it's much easier just to look at it rather than calculate it using the tangent formula. But you can use the inverse tangent formula to get pi as well. So our point over here, r, our point 1 plus I is equal to e, I should write this out, e, or square root of 2 e to the I pi over 4. So I have this here to do my mapping now. So I have my point 1, 1, or 1 plus I is equal square root of 2 e to the I pi over 4. When I square it, according to my formula, r gets squared, so it's equal to 2. And now I have e to the 2 theta. So now I'm going to have e to the I pi over 2, which I'm going to graph that now. This tells me my radius is 2, and my angle is pi over 2. So my angle is over here, right, along this I axis, but radius is 2. So this is 2I is equal to 2 e to the I pi over 2, which means this point here gets mapped to this point here. So that's what this graph is about. And I placed kind of my scratch work over here with the general graph. So I have some z equals r e to the I theta, and then my function on my complex number gives me a new complex number. Here I called it z prime. I think physicists like that. That's okay, right? Then, so my new z prime is equal to a new radius and a new theta prime. I should put a prime here, my new theta. And there's something interesting about this theta here and a theta here. So when you multiply by a theta, what you end up doing is you end up rotating. Because what else would theta do? So let's look at that next. So next I'm going to talk about the three basic types of transformation. The first one is a translation, which amounts to addition of a complex number. The second one is rotation, which is multiplication by a complex number. And finally is reflection, which is taking the complex conjugate. So we'll go through each one of these. We will start with the first type of transformation, and that's translation, addition of a complex number. So if our function w is equal to our complex number z plus a plus bi being our constant that we're adding to z, our complex number. So that's going to add a to, if z is equal to x plus iy, then that's going to add a to x and add b to y. So what that's going to do is translate x by a units to the right and y by b units up. So for example, if we have a function w that takes a complex number z and it's equal to z plus 2 plus 3i, then if z is equal to 1 plus I, then w of z is 1 plus I plus 2 plus 3i, which is equal to 3 plus 4i. Graphing this will take my 1 plus I and map it to 3 plus 4i. So you can see my original point, and I'm just going to put my original point here in blue. It shifted my original point over by this 2 to the right, and then it shifted the y coordinate up 3 to get our new point. So that's translation. Translations are achieved by adding a complex number. Our next type of transformation is rotation, which is achieved by multiplication by a complex number. So if we have a complex number z, which is equal to r e to the I theta, and then we multiply it by a constant, another complex number, which is e to the I theta prime. And at this point, I haven't put another radius in here because I want to focus on the rotation. So let's let r equal 1. So we have e to the I theta prime. What you'll see is this multiplication of two complex numbers. Well, you have your r, then you have your e, and then you're going to have I times theta plus theta prime, just because of the way exponents work. What we see is this new multiplication of the complex number with theta prime rotates the vector counterclockwise by theta prime. So multiplication by r e to the I theta, well, it scales by r, but the theta is a rotation by theta in the counterclockwise direction. So for example, let's let w take a complex number z and then multiply it times 2e to the I pi over 2. So when we write z in terms of our exponential form, r e to the I theta, and multiply by 2e to the I pi over 2, what you can see is, well, first, the two constants, 2 and r, get multiplied together. Then you have e, and when you multiply the exponents, you add the exponents. So you're going to have I times theta plus pi over 2. So this is what I mean by there's a rotation. And let's take z equals to I. So z equals I, and I plot this on a graph to help me get the theta and the r. Well, first it's I, radius is 1, and I can see from the x-axis from here to here is pi over 4 radians. So this is how I write I in my exponential form. Again, you have those formulas where you can plot your z and then use the formula for r, which will be square root of x squared plus y squared, and then theta is the inverse tangent of x over y. But here I can just see it. It's equal to pi over 4. I can plug in my z now into my w. So w of I is equal to e I pi over 4 times 2e pi over 2. So my 1 and 2 here, my radius gets multiplied, and I get 2e to the I pi over 4 plus pi over 2, which is 2e I 3 pi over 4. I can plot now my e I 3 pi over 4. So 3 pi over 4, I go 3/4 of the way around, right? Because 2 pi will get me back to the start. And then I need the radius is now 2. So here I see that 2e I 3 pi over 4 is equal to negative 2i. And again, if I really wanted, I can use my formulas to convert from here to find r and theta. But it's easy, these numbers, pi over 4, it's easy to see just by graphing. And now, oh, I almost missed the point. So here is our original point, I, and you can see when we multiplied by a complex number with a different theta, pi over 2, what we ended up doing is rotating by an additional pi over 2 radians. We rotate our original vector over by pi over 2. So again, multiplication by a complex number is simply a rotation of our vector. And then if we have an r in front of our e to the I pi over 2, that's scaling from r equals 1 to r equals 2. And our last type of transformation is reflection, which is what happens when we take the complex conjugate. So the complex conjugate reflects across the real axis. And here's my example. I kind of kept it. You can kind of see it's like a is equal to 3, b is equal to 2. But if we take ab, 3, 2, and then we make the b negative, what you can see is we have the complex conjugate, and it reflects across this real axis. Our last topic is about extending the domain of some elementary functions, the sine, the exponent, the logarithms, the sinh. So elementary functions of real variables can be extended to deal with complex numbers. And these are the particular functions we're going to look at. We used the Taylor series to extend sine, cosine, the exponential function, and then we got the Euler formula in this form, the z, the exponential form of a complex number. We'll also have these two formulas we can get, the sinh and Cosh, as well as natural log. So let's take a closer look at each of these. First, we'll look at the sine and the cosine. And actually, we worked on this in a previous video, so I'm not going to do all the work, but I have it here for your reference. But I'll just say that we used the Taylor's theorem to expand what sine will look like, and what we found is the polynomial that approximates the sine function is z minus 1 over 3 factorial z cubed plus 1 over 5 factorial z to the 5th minus 1 over 7 factorial z to the 7th, and you keep going for odd numbers, 1 over n factorial z to the n, and the signs alternate. We did not do cosine, but you could do something similar, and you'll see cosine is equal to the even terms, 1 minus 1 over 2 factorial z squared plus 1 over 4 factorial z to the 4th minus 1/6 over z to the 6th plus, and it's 1 over n factorial z to the n. And as I mentioned, we had a detailed explanation of this in the previous video, so I'm not going to go through it, but if you want, you can either refer to this, and maybe that's enough, or go back and look at the other video. In the previous video, we also expanded, using the Taylor series, our exponential function, and we found that's equal to 1 plus z plus 1 over 2 factorial z squared plus 1 over 3 factorial z to the 3rd, all the way up to 1 over n factorial z to the n. So what you see is the odd parts are the sine function, and the even parts are the cosine function, and we got Euler's formula, which is e to the I z equals cosine z plus I sine of z, which we use all the time. And as you see, we also use the exponential form of the complex number all the time. Z equals r e to the I theta, which is equal to r cosine theta plus I sine theta. And again, all of this was derived in the previous video. There are a couple of things about the exponential function that I'd like to say because they're not expected properties. They're different from when e to the x, where x is a real number. So when e to the z, where z is possibly a complex number, well, this is periodic with an imaginary period of I 2 pi. And so, in other words, e to the z plus I 2 pi is equal to e to the z times e to the I 2 pi. And remember, rotating by 2 pi just gets you back to 1. So this is simply equal to e to the z. And we kind of saw that when we were looking at this different way of graphing our functions, which I've already used. So right, when you have e to the I pi, you come around, but by the time you get to 2 pi, you come all the way around. And if you have something like 4 pi, well, you start here, and then at 2 pi, you're back at the same start. When you come around to 4 pi, you're back at the same start. And this, here I increased the radius, but you should think of this as looking down, so it's like a perspective thing, but they're all at the same radius here. The second thing that's a little bit different from real numbers is our e to the z can now be negative because e to the I pi is equal to -1. These two formulas, sine and cosine, in terms of exponents, they're actually the same formulas that you have when they're real numbers, but now, and normally for real numbers we put in x, so e to the ix minus e to the minus ix over 2. But now we're going to put a z instead. So these two formulas will be useful later when we're doing calculating residues, when we do integrals. And also the Sinh and the Cosh formulas are also convenient later when we're doing residues to do integrals. But that's later. They'll be useful later. And the last thing we should look at is the natural log. So natural log of z, if we write z as r e to the I theta, now we can, since this is a multiplication, we can break this up just using properties of logarithms. This is natural log of r, natural log of e to the I theta, which is equal to natural log of r plus, and then this becomes I theta. And I like to include this but I don't think your book usually does. But just to point out that the logarithm is a multi-valued function, so you get the same answer if you add I 2 pi n, again, because e to the I theta is periodic. So n is just a constant, so I 2 pi. So you can add I 2 pi or I 4 pi or I 6 pi. That's what the n is for. You just multiply by not n is a constant, n is an integer, sorry. Some examples of this formula, if you want to evaluate natural log of 1 and natural log of -1. So 1 is equal to 1 times e to the 0. So natural log of 1 is natural log of 1 e to the 0. With this formula, that means it's natural log of 1 times I, and then theta for 1 is just 0. So this whole thing is equal to 0. If you want to evaluate natural log at -1, well, -1 is equal to 1 e to the I pi. So natural log of -1 is natural log of 1 e to the I pi, using this formula here, which is natural log of 1 times I, and then you take theta, which is pi. And then also you just want to remember you can add any multiple of I 2 pi and still have the same answer. But I put this in blue because I don't think your book uses this. But I have it here because, I don't know, because it's technically correct. And maybe your book does use it, I just didn't see it. Anyway, so natural log of 1 is 0, and then you have I pi. And I just put I pi because, again, I think that's what your book has, but this also is technically correct. And now we are ready for our last example of the video. I have another example because logarithms are often motivated by the need to solve problems of the form e to the w is equal to z. You use the logarithm to find out what w is equal to, and w, when you use the logarithm, is equal to natural log of r plus I theta plus I 2 pi n. So the example I have is to find the number z such that e to the z is equal to 1 plus I. So to solve this equation here, e to the z equals 1 plus I, we're going to use a three-step process. The first step is to put the right-hand side over here in exponential form. So 1 plus I if I graph that over here, 1 plus I, now the radius is square root of 2, e to the, if I go all the way here, I'm at pi over 2, so halfway is pi over 4. Or as I say, you can use our formula r is equal square root of x squared plus y squared. In this case, our x and y are both 1, so we have square root of 2. And theta is equal to the inverse tangent of opposite over adjacent, so that's y over x, so that's 1 over 1, which is equal to pi over 4. I'm sorry, I had to remember, I had to say the words to get the formula for tangent, but inverse tangent of 1 over 1, pi over 4. And that's what I have over here. So here r is equal square root of 2. Oh, I actually wrote it over here already. Okay, never mind. There we are. Our second step now is to put the left-hand side over here on the form e to the z equals e to the x, e to the iy. So that's not too hard. So now I have e to the x, e to the iy is equal to, and on the right-hand side, I have square root of 2, e to the I pi over 4. And our third and last step is to equate the right and left-hand side and solve for x and y. So here I have e to the x, the real part, is equal to square root of 2, and the imaginary part, well, I have y is equal to pi over 4. So solving e to the x equals square root of 2, I get x is equal to 1/2 natural log of 2, and I have y equals pi over 4. So that means z is equal to 1/2 natural log of 2 plus I times pi over 4. And technically, I should be able to multiply I 2 pi, any multiple of I 2 pi, or any integer multiple of I 2 pi. To review what we covered in this video, we talked about functions of complex variables, because just as with real variables, complex variables can be related to another using functions. And if we're given two complex variables, w and z may be related. In other words, w may be a function of z, so w of z. And it's common to separate the real and imaginary parts of the function. So if our complex number z is equal to x plus iy, and w is a function of x plus iy, often we like to write w as two functions, u plus I times another function v, or u of xy. So again, u relies on x and y over here, plus I times v, which also relies on x and y. And our example was w of z is equal to z squared, which is equal to x squared minus y squared plus 2ixy. In this case, u would be equal to the x squared minus y squared, and v is equal to whatever is multiplied by I, that's 2xy. And that will give us u and v. They're dependent on real input, and they give you a real output. So these are real valued functions that take real numbers as input. So we can analyze u and v as we would what we did normally in first variable calculus or something. We talked about visualizing or graphing complex functions. Because it takes the entire plane to represent a single complex number, we can't represent a function using one plane. So we need to think of a function as a mapping from one complex z-plane over here, the domain, to another complex w plane, the range. And we did this example of w equals z squared, and we said we would map things like the number -1 would then get mapped to 1, and then I gets mapped to -1, and we could put the arrows, but essentially these points get mapped to these points over here. And there was a second, more abstract visualization, which is to plot two functions u and v, which we talked about before, as the real and imaginary components of w, but we really didn't get into that because this visualization here is what's usually used. Last, we talked about extending the domain of elementary functions. We had used the Taylor series to do the sine, the cosine, and the exponent, and then we have these the Euler formula. We wrote with polar coordinates our complex numbers in terms of an exponential form. We have these formulas for sines and cosines, as well as sinh and cosine, Cosh, which these formulas will become more important later. And then also important now and also important later is this formula for the log of z, which is equal to the natural log of r plus I theta. And that's it for this video. Thank you for watching.